Today, this presentation summarizes the dynamic analysis of a three-story steel shear frame. Structure is treated as a lump mass shear building system because the beam are assumed rigid and axial deformation column is neglected. The main purpose is to determine the fundamental vibration properties. First, natural circular frequency, the corresponding frequency in hertz, the fundamental period, and the first mode shape. The analysis uses the assigned frame geometry and converts it into 3 degrees of freedom lateral model, where each floor level has one horizontal displacement coordinate. Final result is a physical consistent first lateral sway mode, normalized so that the roof displacement is equal to 1. The original frame is simplified into a dynamic model that still captures the important lateral behavior. Because the beams are rigid, each floor moves laterally at a single rigid level. Because axial deformation is neglected, the only dynamic coordinate required are horizontal translation. These are defined as U1, the first floor, U2 for the second floor, and U3 for the roof. This gives 3 degrees of freedom shear building model. The lump masses are calculated from the mass distribution at each floor level. The first floor has the largest mass at 640 kg, followed by the second floor at 520,000 kg, and the roof at 280,000 kg. This idealization is the basis for the mass matrix, stiffness matrix, and equation of motion. Once the model is defined, the next step is to assemble the dynamic matrices. The mass matrix is diagonal because the analysis uses lumped floor masses and no mass coupling is assumed. The stiffness matrix is formed from the story stiffness. First story stiffness is 8.75 meganewton per meter. The second story stiffness is 6.25 meganewton per meter, and the top story stiffness is 4.8148 meganewton per meter. Top story is stiffest because it is the shortest. Equation of motion is mu double dot plus ku equals p of t. For free vibration, the external force is removed and the system becomes a generalized eigenvalue problem. K phi equals lambda m phi, where lambda is equal to omega squared. Fundamental vibration mode obtained using inverse vector iteration. The method begins with an initial estimate where all the floor sway in the same direction. At each iteration, the stiffness matrix is solved against the mass weight previous mode estimate. The result is then normalized so that the roof displacement is equal to 1. The Rayleigh quotient is used to estimate the eigenvalue. The circular frequency is the square root of that eigenvalue. Convergent plot shows that the first estimate is 1.9678 radian per second. Well, the second estimate is already very close at 1.95464 radian per second. In the third iteration onward, the frequency remained essentially stable at 1.9546 radian per second. Final mode shape is a smooth first lateral sway mode. First floor model ordinate is approximately 0.462. Second floor ordinate is approximately 0.928. And the roof ordinate is normalized to 1. Because all the values are positive increase with height, the floor moves in the same lateral direction with the maximum relative displacement at the roof. The frequency was also verified using the generalized model mass and stiffness. The generalized mass is 864,151.68 kilogram, and the generalized stiffness is 30064 times 10 to the 6 Newton per meter. The ratio gives the same circular frequency of 1.95436 radian per second, confirming that the model calculation and inverse iteration results are internally consistent. Thank you.